Let's try now to make a short overview of fractures. This is actually a very extensive and complex subject that goes behind this presentation province. I would suggest to make a reference to the several books and papers published on this subject. A short reference list is reported after the final consideration. In this presentation, we mention only some basic concepts, mainly for people not familiar with the geology. What is a fracture? A fracture can be described as a narrow discontinuity formed as a result of stress. They are generally defined considering the motion that has occurred across the fracture surface during their formation. Extensional fracture is a fracture that shows extension perpendicular to the fracture walls. The term is related to joint or fissure when fractures are open, to veins when fractures are mineral filled, and to dikes when fractures are magma filled. A shear fracture is a fracture for which the relative movement is parallel to the fracture walls. Strictly speaking, the term shear fracture is mainly related to small discontinuities, while the term fault is more commonly utilized for larger shear fractures. An additional kind of discontinuities are the compaction-related fractures called tension gauges. It is a quite particular population of small discontinuities forming in compaction band where grain crushing and a stress-enhanced dissolution generated a volume loss along a discontinuity. This discontinuity is called a stylolite, filled by the residual material and characterized by zigzag shape. Tension gauges are kind of small discontinuities developing perpendicular to stylolite and interpreted as extensional fractures derived from the compressive stress generating the stylolite. Fractures are caused by stresses related to several factors like tectonic forces, overburden pressure, thermal variation, etc. The stresses are generally described by the orientation and magnitudes of three components called principal stresses, which are oriented perpendicular to each other and defined as sigma 1, that is larger than sigma 2, that in turn is larger than sigma 3. Extensional fractures, like joints, ideally develop perpendicular to sigma 3 and thus contain the intermediate and maximum principal stress, sigma 1 and sigma 2. Shear fractures, like faults, typically develop at 20-30 degrees to sigma 1 in conjugate pairs bisected by sigma 1. Tension gauges linked to stylolite derived from the compressive stress and are parallel to sigma 1. The orientation of the principal stresses change in the different regional stress regimes, and accordingly the orientation of the different types of fractures changes as here illustrated. In the normal stress regime, in the reverse stress regime, and in the range faulting stress regime. The different rock deformations lead to different fracture scenarios: fault-related fractures, fault-related fractures, loading-unloading related fractures, etc. The impact of this deformation are in turn conditioned by the different rock characteristics on which they are acting, like bed thickness, porosity, lithology, facies, etc. In faulted context, we can observe, like in the outcrop here reported, fracture intensity higher near faults because of fault-related discontinuities. The fault zone can be regarded as consisting of a central core with good permeability, or poor in case of myelinization, surrounded by a damaged band where the fracture intensity is higher than the hosting rock. The fracture intensity then gradually decreases with distance from the fault wall. So we can attempt to predict fracture intensity in a faulted area by using the distance from the faults. In folded context, the strain can create fractures with a density proportional to the amount of bending, generally quantified as curvature C, that is the inverse of curvature radius R. So, we can attempt to predict fracture intensity in a folded area by using the radius of curvature that describe the rate of change of dip. In fact, an increase of curvature should mean an increase in strain and thus a higher fracture intensity. The impact of faulting and folding is conditioned by the different rock characteristics on which they are acting. Considering the bedding, we observe that joints generally occur at high angle to layering, where commonly terminate at mechanical bed boundaries. These joints form parallel set with a spacing generally wider in thicker beds. So for a given stress, we expect a reduction of the fracture density with the increment of the bed thickness. Considering lithology, we can say that brittle rocks, characterized by low porosity and fine grain size, are more prone to develop fractures with respect to high porous or ductile rocks, which are more likely to deform plastically. As illustrated by the plot on the left, dolomite, for example, is more brittle than limestone, and for a given stress, the fracture intensity is expected to be higher in relation to the dolomite content. Fractures observed on the outcrop support this view and show a substantial difference in the number of fractures for different rocks. For example, in the outcrop illustrated, the stiffness plays a role in the contrast observed of fracture density between the chert nodules and the surrounding limestone. In fact, the stiffer, more brittle rock should show a higher density of fractures than a less brittle rock. Perhaps the so closely spaced fracture observed in the chert of this outcrop can account also for the relatively thin layers defined by the nodules respect to fractures formed in the limestone affected by a larger scale mechanical layering. The different fracture intensity can be observed in the different layers in relation to lithology, grain size and thickness, with the thinnest limestone layers affected by the closest fracture network as highlighted by the cementation. The different mechanical characteristics can be also mirrored in the different facies that consistently can be more or less prone to fracturing. So, in a carbonate reservoir, we can recognize the presence of different environments of deposition, ranging from the platform interior to the reef margin to the slope and to the basin. The fracture intensity and characteristics mirror this variation. So, for example, focusing the attention to the platform and the reef, we can say that when rock underwent to the overburden stress during the burial, the early lithified biohermal features of the reef margin were likely to be more prone to develop fractures than the grainy features of the platform interior, prone to compaction. So different fracturing is expected just in neighboring environments. So the fracture networks result from the combination of several factors. In fact, a fracture network is the result of the whole history a rock has experienced in terms of stress and in relation to the evolving property of the rocks along the time. Several factors can have played a role. From one side, the initial and evolving rock properties, lithological, sedimentological, petrophysical initial features, lithification, timing, status, diagenetic overprint, timing and status. from the other side, the different stresses along the time: regional tectonic stress, local tectonic stress affect folding and or faulting, burial, erosional unloading, thermal stresses related to heating during burial and to cooling during erosion, former stresses legacy. In a reservoir study, fractures can be observed directly at a well scale, both on cores and on the image logs, while, at larger scale, can be observed on the seismic volume as a seismic fault and or subseismic discontinuity, as highlighted by seismic attributes like continuity and curvature. Also, analogs outcrops can represent an important contribution to understand the complexity of the fracture network. However, the selection of reliable analogs is not straightforward, and the risk of comparing apples and oranges is high. Caution has to be utilized with analogs outcrop because fracture systems exposed are bound to be different from the fracture systems which are located at several thousand meters burial depth. The effect of a late-acting process as unloading and weathering should be considered and filtered. Also, production field analogs could represent a very important source of information. However, the definition of an analog is always tricky because fracture systems are affected by very high uncertainties, and there is always an inadequate knowledge about them also after a long production history. Therefore, analogs producing field data have to be utilized in a orderly way. Analog can be useful, but sometimes misleading. In the fracture study, we have to integrate the different scale of the available data defined by direct and indirect observations: well test, PLT, image logs, cores, plugs, thin section. All these tools detect the fracture system, but integrating them across scales as well as across the different disciplines is a major challenge.